Please take a moment to complete the following warm-up. Use your calculator if necessary. Remember, the square root of a number asks us which number squared equals. So in number 1 and number 2, we can easily find number 1, the square root of 25 equals 5, because 5 squared equals 25. And in number 2, we can easily find the square root of 64 equals 8, because 8 squared equals 64. Sometimes they're nice and we can do them in our head. Occasionally they're a little bit more difficult and we need a calculator to help us. In this case, if we are asked to find the square root of 30, we would enter it into our calculator, finding out that it's about equal to 5.48. Again, review for square root. The square root is the square root of a number, written with a radical symbol. We're asking ourselves what number to the second power equals n. In geometry, this is actually why we say squared or square root. The square root of n is the side length of a square with an area equal to n. So we can see a square that has the area equal to n. The side length then is equal to the square root of n. If we know the square root of n times the square root of n is always n. If we multiply two of the same square roots together, we get that number. Numbers that are perfect squares have whole numbers for square roots. A couple of examples might be, in this square the area equals 1 and the square root of 1 is 1. In this square the area is equal to 4 and the square root of 4 is 2, because this is a 2 by 2 square. Square root of 9 is equal to 3. The square root of 16 is equal to 4. And the square root of 25 is equal to 5. It's really nice when things don't work out perfectly like this. We call those perfect squares. But there are numbers that are not perfect squares. For example, 20, 3, 8, and 12 are not perfect squares. Not because they don't make a square, but because their side length is not a perfect whole number. They do make a perfect square even if the area is 20. The side length here being about 4.47. In the square root of 3, our side length is about 1.73. And in the square root of 8, we see about 2.83. And in the square root of 12, we see about 3.46. Each of these square roots was estimated using a calculator. Not the only way to estimate a square root, though. We can estimate a square root simply between two consecutive integers. For example, we can look between two perfect squares. The square root of 45, 45 is not a perfect square, but it's right between 36 and 49, which are perfect squares. So it's between 6 and 7. It's 6 point something. We can also use a calculator to help us round to the nearest 100th by entering in square root of 45. We can find out it's about equal to 6.71, which is of course between 6 and 7, just like we had estimated here in the first example. Sometimes our estimated decimals are nice and neat, other times they are not so neat. So here we take a moment to review terminating, repeating, and infinite decimals. Terminating decimals end. We can see a clear end to their decimal place value. They do not continue, they end at a certain point. They might end in the ones place, the tenths place, the hundredths place, etc. An example of a terminating decimal would be something like the square root of 36, which is 6. Repeating decimals go on forever in a repeating pattern. One that we refer to quite frequently is 1/3, which is equal to 0.3. Here, 0.3, the 3 is our repetend, that's the part that repeats forever. Infinite decimals go on forever without repeating. For example, the square root of 2 is equal to 1.414213562337, and this will continue forever without having any sort of a pattern. A very famous infinite decimal is pi. It does not repeat itself and it goes on forever. These three different types of decimals, terminating, repeating, and infinite, are very important to us when we're talking about irrational numbers. Irrational numbers are infinite decimals that do not repeat. The irrational numbers do not repeat themselves. They cannot be written as a fraction. Some examples would be square root of 2 or pi. This is the opposite of the rational numbers that we discussed in Chapter 1. Rational numbers either end, they are not infinite, or they repeat themselves. Those are the numbers that we can write as a fraction.